Right, this is the fourth lecture from chapter 10 on chemical reactions. And this is the last of the group of reaction types. So we're looking at replacement reactions. Now, there are two kind of subgroups of replacement reactions that we're going to look at. So this is where there's a reaction in which an atom or polyatomic ion is replaced by a different atom or polyatomic ion. Generally, what we're looking at here are ionic compounds. So replacement reactions are generally just ionic compounds that are reacting with each other. Now, they may actually also be ionic compounds that are reacting with new elements. So the first one we're going to look at is actually single replacement reactions. And so here is an example of that. So we've got water, which is actually a covalent compound, as we know, but we are making a ionic compound with potassium hydroxide. So this is an example of a replacement reaction where we have a metal reacting with water, and then that's going to make us an ionic compound. So we swap out, we've got potassium swapping places with parts of the water compound. And so it's kicking out the hydrogen, not all the hydrogen, but some of it, so that we can make this new compound. It's a lot clearer to see in this reaction down here for the replacement reaction, because what we're doing is we're swapping carbon for the iron. And so you can see on this side we've got the carbon, and then we have iron oxide, and after the reaction we have iron and carbon dioxide. So the carbon and the iron swapped places with the bonds with the oxygen. So on this side we have an ionic compound, on this side we have a covalent compound. So like I said, a lot of these replacement reactions are involving ionic compounds. And we can actually predict whether these reactions are going to occur. So we can predict whether a replacement reaction is going to actually happen. So here what we're looking at is aluminum reacting with copper chloride, and that's actually what's in the picture here. So this is a piece of aluminum foil. This is copper chloride, and they've dipped the aluminum in the copper chloride already. So what you're actually seeing here is copper. This is copper that has replaced the aluminum. And so how can we predict that? Well, that's what this diagram here is for. And so if you need this, I will provide this to you for any questions. So if we look on this table, on this diagram, you're going to look for the two metals that are involved. And yes, I know that hydrogen's here. We'll talk about that. So we're going to look for aluminum. So here is aluminum. Let me grab my pen. Disappeared again. So there's our aluminum. And we're going to look for copper. So where is copper? There's copper. All right. So how is this going to work? So as we go up the table, the chemical activity increases. And so if a metal that is in the other compound is below the free one, then the free one will replace it. So what do I mean by that? So copper is down here, it is bound to the chloride, right? So right now these guys are bound together. Copper's way down here, it's low on the list. Aluminum is by itself, and aluminum is way high on the list. So out of all of the metals, lithium, for example, is the most reactive. It has the highest chemical activity. But aluminum's pretty high up there. So since aluminum is by itself in this reaction, it is going to replace copper in the compound that it's in. And so it's going to swap places. So aluminum is going to jump over here and kick calcium out, or I'm sorry, not calcium, copper out. So we're going to get chlorine by itself for a second, and then the aluminum is going to bind to it. So we're actually, I can tell you, it's going to be erase. Let me look real quick. So aluminum is +3, so it would be AlCl3. And then copper hanging out by itself. That's going to be the rest of that reaction. So the higher up on the table over here that an element is, if it's by itself in the reaction, it's going to make the reaction go. If it's low and it's by itself, the reaction will not happen. So for example, gold, if gold is involved in a reaction, if the gold is the one that's free, like aluminum was free, then the reaction won't happen because gold will not be able to replace anything that's in a compound already. So let's take a look. So we're looking for, so any metal will replace, a metal will replace any metal that it is above. So we know that aluminum will replace copper in copper chloride. So will zinc, Zn. So again, here is copper. So will we get the same sort of reaction that we did with aluminum? So aluminum's here. Well, zinc is right below it. So yeah, zinc is right here. Zinc is above copper. And so it will kick copper out, and zinc is going to bind to the chlorine. And so what we would see again, if we have a piece of zinc, the zinc would start to look coppery because it's actually getting a layer of copper on the surface from the zinc getting replaced by the copper that's getting kicked out to bind with the chlorine. Well, let's take a look then at the next one, which is silver. So we've got copper chloride, so copper's here. Let's look for silver. So silver is down here. This time silver is below copper on our chart, which means that this reaction will not happen because silver cannot replace copper. It would have to be above copper on the chart in order for this to work. So that reaction would not happen. The silver would stay silver, the copper chloride would stay as it is, and they just both sit there. Now, very active metals will react with water, and that's because of the hydrogen. So you've got sodium, you've got water, so the sodium will switch and you'll get sodium hydroxide and hydrogen. Okay, so if you have these highly reactive ones up here, and you can see on the table it actually has them marked, anything sodium and above will actually undergo the reaction. So if you've got sodium, calcium, potassium, lithium, and if you go back to the periodic table, those are the ones that are on the periodic table in the alkali metals. 3 of them are that react with water quite violently. These 3 of these are the ones that we talked about in the periodic table lecture that actually catch fire. So they will actually undergo a reaction. The last one to point out is the hydrogen. So you see that hydrogen is here. So in this case, hydrogen does act like a metal for these replacement reactions. And so metals above hydrogen will replace hydrogen to form metal salts. So for example, zinc is higher up on the chart than hydrogen. So when we have hydrogen sulfate, that is going to be turned into zinc sulfate, and then the hydrogen gas will be released. So hydrogen will act as a metal compared to these guys when there are metal reactions going on. So those are single replacement reactions. Like I said, there are other replacement reactions, and the other major one we're going to be looking at are double replacement reactions, sometimes called ion exchange reactions, because these go on between ions only. So we saw with those single replacement reactions that sometimes you can get covalent bonded element, or not elements, compounds like water and carbon dioxide either being swapped out or formed. Here we're dealing only with ions. So this is a reaction that happens when ions of one compound swap with the ions of another. And you can tell that this is happening because if the reaction is occurring, if you have the reaction happening in front of you, you're either going to get a solid. So a precipitate is just a solid that falls out of solution because usually these ions are in solution. They're aqueous, so they have that AQ. You'll get a gas, so it'll bubble, something like hydrogen. Or you'll make water. That one's a little harder sometimes to see because very often these are in aqueous solutions. One of these has to be formed or you didn't get an ion exchange. So you need to get a solid, a gas, or water made in the equation in order to get an ion exchange happening. So the general equation for this is, as you can see, a swap. So you have AX, BY, you end up with AY, BX. So you're just getting an exchange of those ions. So let's take a look at what that would look like. So here you have NaCl and silver fluoride, so sodium chloride, silver fluoride, and after the reaction you have sodium fluoride and silver chloride. So definitely a swap. And in this case, one of these guys over here is going to be a solid precipitate. It would fall out of the solution. And I would put the little, I didn't here, but I would put the little symbols of solid, liquid, gas, aqueous in there to give you an indication. But generally, if you look at these and you see that they're ionic compounds and they're swapping, that gives you a pretty good indication that it's a double replacement reaction. So let's do a little bit of practice. So for these, balance the equations and then identify the type. So these, I have the balance equations solved in the notes section. So right now we're just going to take a look at these to see what kind of equation they are. So here, if you look, what's happening, we're going from two substances, in this case two elements, to one. So this would be what type of reaction? A combination reaction, right? Or a synthesis reaction. Here, what do we have happening? We always just take a look and see what's happening. So if you look on the reactant side, we have aluminum by itself, iron oxide, so iron and oxygen. And then when we look on the product side, we now have aluminum with oxygen and iron. So this tells us that the metals replaced each other. And because there's not two compounds on each side, we know it has to be a single replacement. Double replacement requires both of them to be compounds. Okay. So take a look at this one and see, now you can see on these ones, this is what I was talking about. I will remember to put in solid, liquid, the states. So the rest of these I'm not going to answer. I'll just have you take a look at them and see if you can figure out what kind of reactions these are. And again, the answers will be in the notes section on the PowerPoint. All right, we'll pick up with our next lecture, finishing up with chemical reactions and Avogadro's number.